All right, 2.6 gas math test. This is the PTVN tables. There were 3 PTVN tables on the test and then 2 ideal gas law problems. Let's do 2 PTVN problems together, and then I'll do 1 ideal gas law, and we'll see how you're feeling after that. Here we go. So PTVN tables are all about predicting changes in variables given information about other variables. It's easier if I just show you an example. So let's say that we know that our initial pressure in a gas system was 0.5 atmospheres, and we also know that the initial volume was 2.6 liters. Well, let's say that that gas is compressed down to 1.7 liters, so that volume is going down. We got to ask ourselves, if the volume is going down, what effect should that have on the pressure? Well, that's going to make the pressure go up, right, according to Boyle's law. So if the pressure's going up from 0.5, by the way, we're solving for new pressure here, I should have said that. If our pressure's going up, then we need to start at 0.5 atmospheres and do something to that pressure to make it go up. So whatever our final answer hit is should be bigger than 0.5. So whenever I do PTVN problems, I should start with the thing above the question mark, which is what I did, 0.5 atmospheres, and I'm going to multiply by a ratio of my other numbers. Here I have a ratio of volumes, and I need to decide whether I'm going to put the 2.6 on top and the 1.7 on bottom, or vice versa. What I need to ask myself is, and I've already asked myself this question, is do I want this number here to be bigger than 0.5 or smaller than 0.5? I've already decided that I want it to be bigger, so I need to think I should put the bigger number on top here, 2.6, rather than 1.7, because that's, if I multiply by a fraction that's greater than 1, that's the way that I get my pressure to go up. If I put the 1.7 on top, then this fraction is smaller than 1, and then multiplying anything by that is going to make it go down. So I'm going to put the larger number on top here, 2.6 liters over 1.7 liters. Grab my calculator and I'll do that real quick. 0.5 times 2.6 divided by 1.7, and I get 0.76 liters. Sorry about that, that's 0.76 atmospheres. I strongly recommend that you punch that into a calculator yourself right now, because calculator work might be a little bit tricky for some of us. So if you cannot get that same number, if you don't get it the first time, you need to practice using your calculator, or you need to come in and see me and practice with me working with your calculator. Okay. So there we go. That's how we do this question. Now, what I want to point out here is that it's not the case that we just always put the initial on top. That is not the case. We have to think about what effect we're having on our pressure, or on whatever, like our question mark here is. Right here, our question mark is final pressure. So I need to think, what effect is this change going to have on my pressure? I know that this is a volume decrease, which is causing a pressure increase. So that's why I put the 2.6 on top. I don't put the 2.6 on top because I always put the bigger number on top. I don't put the 2.6 because I always put the initial number on top. It's nothing like that. This is on top because I know that my pressure needs to go up. So I put the bigger number on top when my pressure needs to go up. Okay, let's do another problem here. This one's going to be a little bit more complicated. It's going to have 2 variables changing. All right, let's say that our pressure this time is 1.5 atmospheres, and our temperature at first is 200 Kelvin, but it's going to go up to 250 Kelvin. Let's also say that our volume is 3.2 liters, and let's make that volume go up to 4.6 liters. So imagine what's going on here. Our container is getting bigger, so if we had a syringe, we'd be pulling that syringe back to make the gas take up more space. But at the same time, we're also increasing the temperature. And the question that we have here is, what effect does that have on the pressure? Well, the first thing we need to do is look at the effects, or think about the effects that this is going to have on our pressure, each variable. Our volume, what's happening to it? It's going up from 3.2 to 4.6. And I need to think, what effect does an increase in volume have on my pressure? Well, if I make my gas take up a larger space, there's going to be fewer collisions, and that's going to make my pressure go down. Easy peasy. Now I need to think separately about my temperature. What's happening to my temperature? My temperature is going up. And what effect is that going to have on my pressure? Well, I know that if my temperature is going up, my particles are moving more quickly. And if they're moving more quickly, they're going to collide with the walls of the container more often, thereby making the pressure go up. So take a look at what's happening here. We have my temperature change predicting an increase in pressure, and my volume change in predicting a decrease in pressure. So we don't know which way this is going to go. Is my pressure going to go up? Is my pressure going to go down? We don't really know. The way that we figure it out is we do the math. So just like in the previous problem, we're going to start with the thing that we know. We're going to start with the thing above the question mark, 1.5 atmospheres. And we're going to change that pressure into something either bigger or smaller. Now, one of my students had a really great way to think about this, and I'm actually going to steal this from him. He said, well, let's just do one change at a time. So I'm going to take my 1.5 atmospheres, and I'm just going to pretend that I only have a volume change here. So let's take that 1.5 atmospheres at 3.2 liters, and let's just make it take up more space. Not even change the temperature, just make it take up more space. Well, that way I know for sure that just that change should cause a decrease in pressure. So I'm going to put my smaller number on top for my volume change. 3.2 liters over 4.6 liters. And then I'm just going to punch that into my calculator and figure it out. 1.5 times 3.2 divided by 4.6. So now, if I've only changed the volume, if I've only increased the volume, I know that my pressure is going from 1.5 atmospheres to 1.04 atmospheres. I'm actually going to keep one more decimal here, 1.043. Let's go with that, atmospheres. And then I'm going to take this 1.043 atmospheres, and I'm going to treat this as my new pressure, which I'm then going to make a second change to. Now I'm going to change the temperature. So I've already dealt with the volume. I'm going to go like that. I've already dealt with my volume, so now I just need to deal with my temperature. Let's add a unit in there. Big problem I saw was people not writing units. If you don't write units, it's very hard for me to follow your work. 1.043 atmospheres is my new pressure, and I know that my temperature is increasing here, which is going to cause my pressure to also increase. So whatever my final answer is should be bigger than 1.043. If I want it to be bigger than 1.043, I'm going to put the larger temperature on top, 250 Kelvin over 200 Kelvin. And there we go. I'm going to take that 1.043, I'm going to multiply it by 250, and then I'm going to divide my whole thing by 200. And I'm going to get 1.30 atmospheres. And that is my final answer. Before, the way that I was showing you how to do these problems was I was just doing all of it at once. So I was taking my 1.5 atmospheres, multiplying it by 3.2 liters over 4.6 liters, and then multiplying that by 250 Kelvin over 200 Kelvin. And I think I lost some people there when I had multiple fractions lined up like that. But taking it one at a time seems to make a little bit more sense for some people. So if you struggled with this in the past, try it this way. Try doing it like that. You can revisit that PTVN packet that you should still have. If you don't have it, it's also posted on Google Classroom. You can revisit those problems, take another stab at these. There's also a video, by the way, in the gas law videos document. This is a Google Doc on Google Classroom. And there's a video of a lady, a teacher, going over those exact problems in the PTVN packet that we did in class. And she explains how to use the tables. She talks about it a little bit differently than I do, but maybe you'd find that useful too. Okay, now that we've done two PTVN table problems, let's do an ideal gas law one. So remember, ideal gas law, this is the one where we have PV equals nRT, where R is always the same. R is always 0.0821 liters times atmospheres divided by mole Kelvin. Sorry, moles times Kelvin. Let's take this whole thing, and I'm going to shrink that down. There we go. Okay, so let's do a practice problem here. The way that these work is you're always given three of the variables, P, V, N, T. You're given three of them, and you're asked to solve for the fourth one. So let's say that we have a gas sample that has a pressure of 0.7 atmospheres, a volume of 2.6 liters, a temperature of 45 degrees Celsius, and we want to figure out how many moles of gas are in that sample. Well, the first thing that we should do is we should recognize that this 45 degrees Celsius needs to be changed to Kelvin. I need to do that right away. There were a few people on the test who forgot to do this, and that cost you some points there. So this should be 318 Kelvin instead of 45 degrees Celsius. If I plug 45 degrees Celsius into my equation, it's not going to work. So now I have all of my variables in a usable format, and I also have my R. So now I'm just going to take my PV equals nRT, and I'm going to rearrange this to solve for N, because that's what I want to get by itself. If I want to get N by itself, then the first thing I should do is divide nRT by RT, and this will cancel out the R and the T. But if I do that on the right side, I need to also do that on the left side. So let's rewrite that as pressure times volume divided by R times T equals N. So that's my setup for this. I'm just going to plug in my pressure, my volume, my gas constant R, and T. So let's do that. Pressure, what is my pressure? 0.7 atmospheres, 0.7 atm, times volume. My volume is 2.6 liters, divided by my temperature is 318 Kelvin. And I'm actually going to do my R separately. That's what that guy in the video did, where he took his R out of the fraction and dealt with it separately, because R has an ugly unit like this. So he said it would be easier if you just took it out and dealt with it separately. Now this time R is on the bottom, which means that I'm going to take my value for R, which is the same every time, and I'm going to flip it. So I'm going to put 0.0821 liters times atmospheres on the bottom instead of on the top like it is here. And then I'm going to put mole times Kelvin on top. And there we go. This is our setup. N equals 0.7 atmospheres times 2.6 liters divided by 318 Kelvin times 1 over 0.0821. So now I'm just going to plug this into my calculator. Again, practice doing this with me. If you did poorly on the test, I'm going to type 0.7 times 2.6 divided by 318 divided by 0.0821. And when I do this math, I get that my n is equal to 0.0697, which I'm going to round to 0.07 moles is my value for n there. And there we go. That's how you do these problems. There are also videos, if you did not like this or you need more practice, if you go back to that gas law videos sheet, then there is an entire video, entire 3 videos actually, of practice problems and explanations for ideal gas law stuff. Please look at those if you are struggling. Ideal gas law videos. If you go to the gas law videos document in Google Classroom. There you go. Okay, so hopefully that is helpful for 2.6 gas math.